Today we're going to talk about the concept of stiffness and stiffness matrix, just to touch upon the fundamental ideas. So first of all, let's define what we mean by stiffness, and specifically stiffness at a point. So the stiffness at a point is the relationship between force and displacement, specifically the ratio between the increment in force corresponding to an increment in displacement. So basically, how much force divided by how much displacement you get at a given point. One way to think about this is to think of the increment in displacement as a unit, and then from there it comes out that one way to think about stiffness is that stiffness is the force needed to induce a unit displacement. And this definition is going to be extremely useful, and you will see that in the next few minutes. Okay, so what is stiffness? Stiffness is the ratio of force to displacement at a given point. You can also think about it in terms of increment. So stiffness is the ratio of the increment in force divided by the increment in displacement. If you make that increment in displacement equal to 1 unit, then the stiffness is the increment in force needed to create a unit increment in displacement. And this can be applied to any linear elastic structure. It could be a beam, a frame, a truss, or a general two-dimensional, three-dimensional generic structure, right? Stiffness is always the ratio between the applied force and the displacement generated by that force. The structure could be in its undeformed position, or if it's not in its undeformed position and some forces have already been applied, then, as I mentioned before, you can think about this ratio as an increment, right? Increment in force divided by increment in displacement, and that delta is the typical mathematical symbol of increment. How does this relate to a concept that we've already seen before, which is flexibility? So the flexibility, as you may remember, right, is the displacement due to a unit force. The stiffness, on the other hand, is the force needed to induce a unit displacement. So flexibility, displacement due to a unit force, stiffness, force needed to induce a unit displacement. If you work out the math, you can see how they are inverse of each other, reciprocals, right? So the stiffness is 1 over the flexibility. You can see that, right? Fairly easy. If you have F equals to Kx and you set X equals to 1, obviously then you get flexibility equals, I'm sorry, this is force, right? Force equals to stiffness times displacement. Then when displacement equals to 1, force equals stiffness, right? And on the other hand, when P equals to 1, then X, right, becomes 1 over K. And that displacement due to a unit force is what we call flexibility. The force needed to create a unit displacement is what we call stiffness. Okay? So they are reciprocals of each other. The second concept that is going to be very important here is the idea of degrees of freedom. So what are degrees of freedom of a structure? Simply said, degrees of freedom are simply all the independent displacements of interest. So you take a structure, you select a number of points that you are interested in, and those are your degrees of freedom. All the independent displacements associated with those points are indeed your degrees of freedom. So if you think about a simple cantilever beam here with two nodes of interest, you have 6 degrees of freedom. One horizontal displacement, one vertical displacement, and one rotation for every node. If you take a simple space truss here, you have 6 degrees of freedom as well. 2 displacements per node, and then you have 3 nodes, so that boils down to 6. In a more complicated structure here, like a 2-story frame with rigid connections among all the members, and let's say we are interested in the displacement at all the end points of each member, then we see that we have 3 degrees of freedom per joint, 1 horizontal, 1 vertical, and 1 rotation. We have 4 joints, so that's 3 times 4, that's 12, plus 2 rotations at the base, because we have hinges for support, so the only free motion, free displacement is the rotation. So that gives you 14 degrees of freedom, right? With 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Obviously, there are more elaborate definitions of degrees of freedom depending on what you are doing, and we are going to expand on those definitions later on. But basically, at this point, a general definition that will be useful for our purposes is that all independent displacements of interest, that's what we call degrees of freedom. Okay. Very well. So we have the concept of stiffness at a point, which is applicable to any structural system, so long as it's linear and elastic. We have the concept of flexibility and stiffness and how they are reciprocals of each other, and then the idea of degrees of freedom. Now, what is a stiffness matrix? A stiffness matrix, if we think of a structure that has multiple degrees of freedom, stiffness matrix is nothing more than a relationship between the forces at all degrees of freedom and the displacements, again, at all degrees of freedom. So now we are thinking, right, that forces not only create displacements at a point where they are applied, they also create displacements at other points. And so we need to account for the relationship between those, right? And so for a simple space truss like this, and before I go any further, obviously remember that all these forces must and absolutely be in equilibrium. That's non-negotiable. Okay, so in this specific example, let's say we have 6 degrees of freedom, and we have those displacements here, 1 through 6, and we have our 6 forces, 1 through 6. The stiffness matrix is a matrix that is 6 by 6, and it relates those 6 displacements to the 6 forces. So if I give you 6 displacements that you are going to apply at at these three joints, right? So I give you all of them, 1 through 6. If you multiply that vector of displacement, you pre-multiply by the stiffness matrix, which is 6 by 6, you're going to get a vector which is 6 by 1. Now that vector, the meaning of that vector is those are the forces that you need to apply at all 6 degrees of freedom in order to make those 6 displacements come about. So if you want to generate those 6 displacements simultaneously at all 6 degrees of freedom, these 6 forces are the ones that you need to apply. And how to get those forces is by multiplying the stiffness matrix of that system by the displacements. Okay? Now, this is all fine, but there is one thing I haven't told you about yet, which is how do you get the stiffness matrix? Well, here I'm going to show you one procedure, which is not necessarily the most efficient one, but it's the one that we're going to explore first. So if we remember our matrix multiplication, we realize that if I give you a matrix, let's just say here, for example, a 4 by 4, and I multiply that matrix by a vector, which is 0 everywhere, except at one position. Let's say in this case is the first position. Then when I multiply that matrix times that vector, what I am going to recover is the first column of that matrix, right? Just by simple matrix multiplication, you can see that what's going to come out here on the left side is the first column of that matrix. So how can that help us to determine the flexibility matrix of a structure? Well, the way that that helps us is that you can see that the nth column, n being any number from 1 to the total number of degrees of freedom, the nth column of the stiffness matrix corresponds to the forces needed to induce a displacement of 1 at degree of freedom n and a displacement of 0 at all other degrees of freedom. So we can use what we know about computing deformations in structures in order to compute the stiffness matrix of a system. And we're going to start doing that on a very simple but illustrative example. Let's review what we know about ideal springs, right? A spring with constant K is basically a simple element in which the force and the displacement are related to each other via the stiffness of the spring, stiffness constant, right? So if you want to create a relative displacement, delta, between the 2 points, right? This is relative displacement between the 2 points. You have to apply a force P equals to K times delta, okay? We all know that. And so how do we apply this idea to determine the stiffness matrix of a spring? So first of all, realize that an idealized spring in space, let's say we're talking about one-dimensional behavior here, so the spring can only deform along its line, has 2 degrees of freedom. Displacement at one end, let's call that end 1, and displacement at the other end, let's call that end 2. So what we're looking for is a 2 by 2 stiffness matrix that relates the 2 displacements to the 2 forces that have to be applied at the 2 ends. Now how do we do that? We do that by using this definition. So if we want to determine the first column of the stiffness matrix, we apply a unit displacement at end 1, and we find the forces that are needed to induce that displacement by using the what we know about the behavior of an ideal spring, we can see here that in this case the relative displacement is 1. The displacement 1 is going to the right, it's positive, so the forces that are needed are as shown here in red. K going to the right in one end and K going to the left in another. And so those forces form the first column of the stiffness matrix. We do a similar analysis for end number 2, and in order to induce a unit positive displacement at end 2, we need forces K and minus K as shown here. So we place negative K at degree of freedom 1 and positive K at degree of freedom 2. And that gives us the stiffness matrix of a spring. So if I told you, let's say as an example, that I have a spring here with stiffness K and I displaced one end by 3 units and I displaced the other end by 8 units, I can find the force needed to make that happen. What is the force? Well, we already know our stiffness matrix that looks like this, and we multiply that by these displacements, 3 and 8. And what we get, right, is 3K minus 8K, and then minus 3K plus 8K. That comes out to minus 5K and 5K. So basically, in order to make those displacements happen, we need to apply a force here on this end, which is going this way with 5K, and at this end this way with 5K. And if we apply that, we are going to get a relative displacement of 5. Makes sense, right? 5K divided by K gives you 5. And so that makes perfect sense, right? This gives you a way to determine the forces given the displacements at the degrees of freedom. We can extend this to more complicated systems. So let's say we have 2 springs connected and we see that each one has a different stiffness, let's say K1 and K2. We apply the same concept. So the first column is going to come about by applying a unit displacement at degree of freedom 1 and 0 at 2 and 3. If we find the forces needed to make that happen, we see here that we need a force K1 at degree of freedom 1 and negative K1 at degree of freedom 2. No force is needed at degree of freedom 3 because, as you can see, the spring K2 is not elongated or shortened, so there is no force associated at degree of freedom 3. So then that gives us here in yellow, you can see the first column. Then you do a same analysis with the second column, second degree of freedom. And so now this one gets a little more, just a tiny bit more involved. So if you are going to induce a unit displacement at degree of freedom 2, you have to move both springs, K1 and K2, right? Because they're connected at that point. So the force that you need is K1 plus K2. And then you need minus K1 in the left end and negative K2 at the right end. So that gives you the second column here in yellow, and similarly the third column in green. And that gives you the stiffness matrix of the whole system. And now, again, if I gave you the displacements at degree of freedom 1, 2, and 3, and I asked you what forces do I need to make those 3 displacements happen, the answer is multiply the stiffness times the displacements, and you're going to get the force. right? So the stiffness matrix contains the information regarding the forces needed to induce any arbitrary displacement. And the way that we compute that matrix is by applying unit displacements separately, right, at every degree of freedom and 0 everywhere else. And that gives us every column of the stiffness matrix, and once we have that assembled, we can use that for any other displacement. The reason this works, right, is because we are working on the underlying assumption that the system is linear, so scaling is permitted. Okay, now another quick interesting thing here before we finish is that, as you can see, for this system our matrix is 3 by 3, and maybe you've already noticed this, but in case you haven't, the stiffness matrix of the whole thing, as we just found out, is K1 minus K1 0 minus K1 K1 plus K2 minus K2 0 minus K2 K2. Now think about that. That matrix is basically a superposition of the individual stiffness matrices of the individual members, right? So if you think of this, let's change to a different color. You have K2 minus K2 minus K2 K2. And here they are adding, right? Because they are joint, right? So this is extremely important, because what this is telling us is that by knowing the individual stiffness matrix of every component and how those components are connected, we can assemble the stiffness matrix of the whole system. That's an extremely useful and important property. We're going to talk more about it, but I just want to leave you with that so you can think about it. If you had more springs, let's say, connected in the same way in series, you could easily come up with the stiffness matrix of something like this. By just using what we just learned. You could say K1 minus K1 0 0 minus K1 K1 plus K2 sorry, this one goes here. Minus K2 K2 plus K3 minus K3 0 0 minus K3 K3. I want you to take a look at this and make sure you understand what's going on there, right? These are basically the degrees of freedom. 1, 2, 3, 4. So we have 4 columns. Each one of those columns can be found by applying a unit displacement on that degree of freedom, 0 everywhere else, and finding the forces needed to make that displacement happen. Very well. See you next time.